Hi there. Welcome to Introduction to Basic Pulley Systems. This video tutorial is designed for folks who have progressed in an outdoor sport to the point where you're starting to learn about rescue scenarios, which often involve pulley systems. If you find yourself needing to construct pulley systems but haven't even thought about pulleys since that science class 15 years ago, this tutorial is for you. The point of this tutorial is to illustrate the concepts behind how pulley systems work, and also how they don't work. This is an introductory video, and the point is not to be precise. Rather, it's to help you use some real-world examples to understand the basic concepts of pulley systems. If you're a scientist or maybe an architect, you might be uncomfortable with approximate math or imprecise terminology. And yes, in some contexts, precision is critically important, like when you're pushing your gear to the edge of its rated strength. Precision is also helpful in deepening our understanding of the many aspects of physics that help or hinder our objectives. But at the introductory level, precision can get in the way of understanding foundational concepts. So, for the purpose of this tutorial, we'll acknowledge that our numbers and terms are approximate, and we'll focus on conceptual understanding. So let's get started. First, we need to talk about two uses of the term pulley. A pulley is a piece of gear designed to reduce friction with the inclusion of a wheel that facilitates rope travel around a bend. Friction is a mechanical disadvantage, so a pulley reduces the mechanical disadvantage by making a rope glide smoothly around a bend. You may encounter a double pulley, and there are even examples of pulleys being built into gear like carabiners. A pulley improves the efficiency of a system. A pulley system, on the other hand, is a rope system that multiplies the pulling force on an object through specific configurations of rope passing through the object and through a stationary anchor. The mechanical advantage of a pulley system is solely a function of the rope configuration. A pulley system can function with or without pulleys. However, these are two pictures of efficient pulley systems because they employ pulleys, the piece of gear, at each rope turn to maximize mechanical advantage. We'll talk more about this later, but it's important to understand the difference between the two uses of the term pulley. Let's put science aside for a moment and look at some things most of us are familiar with: buckets of rocks and a gazebo. Here, we have 4 50-pound buckets of rocks, and the task is to move the rocks onto the gazebo. Let's assume none of us are strong enough to simply pick up the bucket and put it on the gazebo. Let's take a look at the different ways our cartoon friends approach this task. First, we have Ryan. Ryan decides he's going to pick up the bucket and carry it up the stairs. The bucket weighs 50 pounds, and Ryan will be lifting 50 pounds. Linus isn't so sure about carrying 50 pounds, so he recruits his twin, Lucas, and together they carry the bucket up the stairs. In this case, the 50-pound load is shared between Linus and Lucas, so they are each carrying 25 pounds. Mary and Lindsay have a different idea. Rather than awkwardly carrying a bucket up the stairs together, they've introduced a rope into their plan. With each holding one end of the rope, they are sharing the 50-pound load, so that each of them only needs to lift 25 pounds. You can imagine if they each had their own ropes tied to the bucket, the outcome would be the same. In this case, the single rope passed through the handle of the bucket has the same effect as 2 individual ropes. Now let's move over to Ron. Ron doesn't have anyone to help, but he also doesn't want to lift 50 pounds by himself. He's able to employ the help of a bolt anchor in the ceiling of the gazebo to support half the weight, using the same rope configuration as Mary and Lindsay. Here's where we can talk about the way forces travel along a rope. If Ron puts 25 pounds of upward force on that rope, the entire length of rope will have 25 pounds of force on it. So in this case, Ron's 25 pounds of force travels around the handle and back up towards the bolt anchor. The effect is that the anchor is holding half the weight of the bucket, while Ron holds the other half. There are two things going on here: load sharing, or weight distribution between Ron and the anchor, as well as a multiplication of forces. Ron's 25 pounds of upward force gets doubled as it travels around the bucket, creating the effect of 2 ropes each holding 25 pounds for a total of 50 pounds to lift the bucket. Ultimately, there are 2 units of output, or 50 pounds, for every 1 unit of input, Ron's 25 pounds of force. This is a 2-to-1 pulley system. Let's take a brief break, look at some puppies, and discuss some concepts that would make our conversation more precise. You may have noticed we've been using a 50-pound bucket as a baseline in our examples. Well, pounds is a unit of weight, which is a static measurement, meaning not one that's moving. But in pulley systems, our goal is to move things. What would it take for these dogs to pull the walker? It's the movement of their weight against the walkers, their force, that will pull the walker. Certainly weight is a key piece of the equation. Imagine a child walking these dogs. It would take much less force for them to pull the child off their feet. Imagine a small dog trying to pull the walker. They likely couldn't generate enough force to do so. The simple formula for force is mass times acceleration. How much does it weigh and how fast is it moving? And we measure force in newtons or kilonewtons. This isn't important for the purpose of our illustrations, but it is important that you understand the difference between weight and force, and that you are familiar with the term kilonewton, since that is the unit in which most of the gear you'll use will be rated for. One more thing to consider: what if this dog walker was walking on a beach? It might be easier for her to resist the dog's pulling and require more force from the dogs. What if she was walking on wet grass? She might have a harder time resisting. This is where friction comes into play. In dog sledding, there are several things that make the dog's pulling more efficient. First, the sled is on skis, designed to slide on snow. Frozen water provides a slippery surface for the skis. In this picture, gravity is also helping as the dogs are pulling downhill. Let's return quickly to Ron's 2-to-1 pulley system. Ron has the rope going around the handle of the bucket, which undoubtedly adds friction. While he still gets the mechanical advantage, the friction reduces the advantage slightly, and he'd have a slightly easier time if there were a pulley on the bucket. Here at the blue gazebo, we have Sandra and Peter. Each of them has a rope and a pulley, but they'll use them in different ways. Sandra puts the pulley on the bucket and attaches the end of the rope to the bolt anchor at the top of the gazebo. This is exactly the same configuration that Ron had on the previous gazebo, only she added a pulley, which we just learned makes it more efficient by reducing friction. Peter decides to put the pulley on the anchor and to attach the rope to the bucket. Peter, too, benefits from the efficiency of a pulley, and he has the added advantage of gravity. While Sandra has to pull up, Peter gets to pull down and will be able to use his weight to help. At first, it may look like Peter has the smarter configuration. But let's look closely at Peter's setup. He has just one rope going to the bucket, as opposed to Sandra's 2 ropes. This makes load sharing impossible. All of the load is going to just one rope. We know from looking at Ron's configuration, and through the idea of load sharing, that Sandra will need to lift just 25 pounds. That force will travel through to the other side of the rope, and the anchor will support the other 25 pounds, allowing her to lift the 50-pound bucket. Let's look at what happens when Peter puts 25 pounds of force on the rope. That force travels along the rope, putting 25 pounds of force on the rope attached to the bucket, not enough to lift the bucket. In this case, while the pulley is helping to reduce friction, the positioning of it simply serves as a redirect, and it does not provide mechanical advantage. With only one strand of rope on the bucket, in order to lift 50 pounds, Peter will have to generate 50 pounds of pulling force. This is known as a 1-to-1, 1 unit of output per 1 unit of input. And if we apply the principles of multiplication of forces, we can also see that there is 100 pounds of force being generated on the anchor, 50 from each rope. Now, one of the things you might be asking is, even though Sandra's bolt anchor can hold half the weight once the bucket is suspended, the bolt isn't doing any pulling, only Sandra is pulling. So how is it that she only has to pull half the weight? This is a great question, and the answer has to do with distribution or displacement of work. Let's look at an analogy. Here we have a mountain and a hiker. The hiker is taking the most direct route up the mountain. It appears to be both the shortest and the steepest route. The hiker appears to be working pretty hard, but she also must be pretty strong to hike at that steep grade. This hiker, on the other hand, has chosen the longer, more meandering, but less grueling route, the switchbacks. Let's just imagine that each hiker weighs 200 pounds, including their pack weight. Both hikers have the same amount of work to do. They both have to carry 200 pounds up 5,000 feet. Hiker A has chosen the path that requires more power as she climbs 1,000 feet per mile. Hiker B has chosen the path that requires less power as she climbs just 500 feet per mile, half the gradient. The trade-off is that while Hiker B will need to exert half as much power as Hiker A, she will need to travel twice as far. So let's take that concept back to our friends Sandra and Peter. It looks like the gazebo is about 3 feet off the ground. Peter's rope is tied to the bucket, so as he pulls down, the bucket will travel up. As Peter pulls down on his rope, with 50 pounds of force, he'll need to pull it 3 feet in order to raise the bucket 3 feet. This is consistent with the idea of a 1-to-1, 3 feet of rope pulled for 3 feet of distance traveled. But let's imagine what happens when Sandra pulls. The bucket is not on a fixed point on the rope, so as she pulls, gravity will keep the bucket in the lowest point on the rope, and the lowest point will continue to change. As she pulls up, the bucket will begin to migrate closer to the bolt, or said differently, the distance between the bolt and the bucket will begin to close. As Sandra pulls up 1 foot of rope, the bucket will simultaneously move towards her and up towards the bolt, splitting the difference so that it moves 6 inches up towards the bolt and 6 inches up towards her, raising it 6 inches off the ground. If Sandra raises the bucket 6 inches off the ground for every 1 foot she pulls, this means that she will have to pull 6 feet of rope for the bucket to lift 3 feet. Said differently, since the bucket is on both ropes, Sandra will need to take 3 feet out of each rope in order to move the bucket up 3 feet. Since it's all one rope, 3 feet plus 3 feet is 6 feet, and that is what Sandra will need to pull. This is aligned with our 2-to-1 pulley system. Just like in our switchbacks example, the work needed is unchanging. In this case, getting a 50-pound bucket to the floor of the gazebo is the work. It can be done with 50 pounds of force over 3 feet or with 25 pounds of force over 6 feet. Let's go see Omar and Jordan at the green gazebo. Omar wants to help, but he can't reach the top of the gazebo, so he offers to hold the pulley up so that Jordan can use it to lift the bucket. With only 1 rope going to the bucket, we know that Jordan will have to generate 50 pounds of force on the rope to lift the bucket. Once that bucket is suspended, Omar will be holding a 50-pound bucket while Jordan is putting 50 pounds of force onto the other rope. Omar will suddenly have to hold 100 pounds. He almost certainly will drop the pulley. This is an important lesson because when we're focused on giving ourselves a mechanical advantage to move something heavy, we can often overlook the impact our system might have on the anchor we're using. Charles over here at the yellow gazebo has combined good ideas to make life easy for himself. With 2 ceiling anchors, Charles has attached the rope to one anchor, a pulley to the bucket, and a pulley to the other ceiling anchor. With 2 ropes on the bucket, we know the load is divided in half. If Charles puts 25 pounds of force on his rope, we know that force will travel throughout the whole rope, with 50 going to the bucket, enough to lift it. Charles has built a 2-to-1 pulley system. By using pulleys, Charles has gained efficiency by reducing friction, and by using a redirect pulley on the second ceiling anchor, Charles has given himself the advantage of gravity. And, thanks to load sharing, the gazebo ceiling is only burdened with 25 pounds on one anchor and 50 on the second. Finally, we'll visit Miranda at the pink gazebo. Miranda has an extra heavy bucket of rocks, 75 pounds, but she's made even better use of her 2 ceiling anchors. She's attached a pulley to both, and rather than attaching her rope to one of them, she first tied the end of her rope to the bucket, running it through the ceiling pulley, back down to a pulley on the bucket, and back to the second ceiling pulley. We can now count 3 ropes going to the bucket. This means that the load is divided by 3. 75 divided by 3 is 25, so Miranda will need to pull with 25 pounds of force to lift this 75-pound bucket. She has created a 3-to-1 mechanical advantage. Now we can apply Miranda's example to the more accurate terminology that you'll encounter as you practice with pulleys. Miranda is applying 1 unit of force or tension to the rope. That unit travels over the ceiling pulley, down to the bucket pulley, and up to the second ceiling pulley. You can see that the bucket pulley has 2 units of tension applied to it, shared by the 2 middle ropes. that 1 unit of tension on the rope travels over the second ceiling pulley back down to the bucket where it's tied. So the bucket receives 1 unit of tension from the end rope and 2 units of tension from the bucket pulley. The force applied to the bucket in the form of tension is 3 units. Let's review some key concepts in this tutorial. First, pulley systems use a configuration of ropes to share the load of an object, or said differently, to multiply the forces on that object. A pulley is a piece of gear equipped with a wheel to reduce friction. Pulleys aid in the efficiency of a pulley system, but they are not necessary for the multiplication of forces or sharing of the load. Now comes the fun part. Find a tree or something strong to hang an anchor off of, and find something heavy. Play around with each of these simple pulley systems and experience for yourself the difference between each of them. This tutorial focused only on simple pulley systems. Undoubtedly, you'll learn compound pulley systems, maybe even right off the bat. While each pulley system is unique, these concepts apply to all of them. Take your time becoming familiar with these concepts and have fun getting creative with pulleys.